Okay, so well, thank you very much for the introduction, and thank you, Guido and Sebastian, for inviting me here today. It's an honor and a pleasure to be here. I'm very excited actually to be within such an interdisciplinary group. So it's a good change from the usual. I'm normally surrounded by engineers and computer scientists, and it's hard on every day. So yeah, so I'm yeah. So thank you for the introduction. I'm from the University of Essex, in particular from the uh, the brain-computer interfaces and neuroengineering lab. My research, in fact, is mostly focused on brain-computer interfaces. So just a brief history about of our lab. So the lab formed about 20 years ago, I think, maybe, I don't remember. And we were just a small group of two, three researchers, just trying some EEG stuff. And then it has become, for sure, the largest in the UK in terms of number of researchers, but also in terms of publications and equipment we have in our lab. Also maybe in Europe, we are centered between the largest groups in BCI. Okay, so today, okay, so what I'll do is I will give a talk about the use of neurotechnologies for cognitive enhancement or cognitive augmentation. And then I will give some first a very broad overview of what are the most typically used neurotechnologies for that. I will focus on actual devices, so I'm not covering like neuropharmacology, for example. And then I will focus particularly on brain-computer interfaces, simply because that's the area I'm most expert on. And then I will talk also about some of the research I do on collaborative BCI. And then we'll cover briefly, depending also on time, it depends how good I am, on other on our other neurotechnology applications. And finally, we'll cover about neuroethics. Okay, so what is cognitive augmentation? Sebastian earlier has given a definition, which is not very different from this definition, which is my definition, but it's basically what is normally meant by cognitive augmentation. So it's the improvement of the processing of acquiring knowledge, understanding, and interacting with the world around us. Such processes encompass communication, attention, the formation of knowledge, memory, judgment, and evaluation, reasoning and computation, problem solving and decision making, as well as comprehension and production of language. So covers really a lot about everything about cognition, cognitive processes, and communication. So I will give a quite broad overview of the devices that can be used for cognitive augmentation. Of course, nowadays there is a quite large use of these technologies. And we can say that there is a well, they are both used, of course, for clinical purposes, for research in many different areas. Also now you can find devices that you can buy from Amazon, for example. We were talking about this yesterday with Sebastian. Sebastian himself has used an EEG set for gaming, or yeah, but you can buy even transcranial stimulation devices from Amazon, for example, for at a quite cheap price. So they are very much used. So for whether or not these technologies can be used realistically for cognitive augmentation depends on a number of factors. And realistically used, by realistically used, I mean like a lot of use in everyday life. So there is a lot of work now on using neurotechnologies in the real world. So how can we use them for improving our memory or monitoring our attention and so on. So, how much we can do this depends also first how effective they are at detecting interpretable neural activity or stimulating specific areas of the brain, how much invasive they are, how portable and expensive they are, and also, how good they are actually at detecting the neural activity if they record the neural activity. And so these are the main factors that influence the use or potential use in everyday life. So neurotechnologies can be broadly divided in recording technologies, so those that record, we will see a few examples, record the brain activity, those that stimulate the brain activity, and then orthogonal to this, we have a distinction between invasive devices and non-invasive devices. The invasive devices are those that are actually implanted in our brain. Again, we will see a few examples of those. So these are non-invasive technologies, examples, the most typical non-invasive technologies used for brain, for recording the brain activity. Again, how good or bad they are depends on like a perspective and on a number of factors. So we talked about being good at actually detecting the signal, so the signal to noise ratio, but also how bulky, how expensive they are, if we want to use them in everyday life. And the resolution, so spatial resolution, so how good these technologies are at detecting the differences in the differences in activity in the different areas, nearby areas of the brain, and also the spatial resolution, the temporal resolution. How good they are at tracking temporal changes. And for example, probably the most typically used device is the electroencephalogram. For example, in brain-computer interfaces research is definitely the most used, and the reason is that it's easier to use, it's portable, it's quite relatively quick to set up. So it's got a number of advantages, very good temporal resolution, but it's very low in a signal to noise ratio, meaning that the signal that you detect is very noisy, very, very noisy. And so in fact, a lot of work into BCI goes into cleaning that signal, filtering that signal so that then it can be used, the features can be extracted. And then we have functional near-infrared spectroscopy, which is based on detection through near-infrared spectroscopy, detect changes in activity in the brain, in the oxygenation of the brain, similar to this. So changing the different changes in, detecting changes in the oxygen in the brain is the fMRI, so functional magnetic resonance imaging. And then there is the MAG, which is also about detecting, like EEG, detecting the neural electrical activity of the neurons. But as you can see, for example, MAG and fMRI, they're definitely not portable and not very easy to use, very expensive, especially fMRI to use. But fMRI, for example, is very good at, it's got a very high spatial resolution, but not temporal resolution, and so on. So in brain-computer interfaces, in particular, EEG and also now fNIRS are most typically used. And then for brain stimulation, we have, the most typical devices, the most used are definitely transcranial electric stimulation, and transcranial magnetic stimulation. Again, they have advantages and disadvantages, and also in terms of how cheap or portable they are, but also in terms of the spatial and temporal, well, spatial resolution, sorry, not temporal. Yeah, and then the transcranial focused ultrasound stimulation is less used and is still not quite known about the the effects that it can have on humans, for example. But it's very precise in terms of what areas it can stimulate. While, for example, transcranial magnetic stimulation has got a very lower spatial resolution. So these are more or less the, well, sorry, if I go back a moment. These are the non-invasive devices. The stimulation devices are, well, are considered non-invasive. However, it depends on whether, well, the devices, of course, are external to the brain, but the effect they have is in the brain. So one can argue whether they are invasive or not. But then we definitely have the invasive technologies. So these are electrodes, well, implanted electrodes typically. So the electrocorticography, sorry, which is arrays of electrodes laying on the surface of the brain. Microelectrodes, which are actually implanted in the brain. And then we have, for example, deep brain stimulation, which is normally used for, well, all of them are used for clinical purposes. In fact, it's very important to understand that. So invasive neurotechnologies are much more accurate in terms of detecting the neural activity. And it's like, for example, for brain-computer interfaces, researchers using invasive technologies have much better results than those using non-invasive technologies. However, you don't implant electrodes just for running a BCI experiment. And so these are only used with patients who have them implanted for clinical reasons, for example, for controlling seizures or like deep brain stimulation, I don't know, for patients with Parkinson's and so on. Yeah, so for like maybe in the future, not very far, we will be able to have invasive devices that, like nanotechnologies that are easy to implant, but for the moment, this is not the case. And so it's just typically we use non-invasive devices. This is just a plot showing, what an ideal device would be based on whether it's invasive or not, their temporal resolution and the spatial resolution, and also how portable they are, so how easy they are to use in everyday life. So an ideal one would be up here, and then you have them spread all around. Yeah, so as I said, EEG, electroencephalograms, are definitely the devices that are used most typically for cognitive augmentation and in experiments aimed at developing devices for in everyday life. Okay, so yeah, so I will now focus on neurotechnologies, so applications for communication, in particular for BCI. There are, of course, cognitive enhancement also cover much more than this, and if I have time, I will cover some of those. But yeah, memory enhancement, attention monitoring enhancement, situational awareness, social interaction and hyperscanning, Yeah, so there is all sorts of things, really, emotion, recognition, for example. But for the moment, I will focus on brain-computer interfaces. So a definition of, a traditional definition of brain-computer interfaces is a device that converts brain signals into commands for external devices. This was the original, well, the most traditional use of brain-computer interfaces, and initially they were developed for this use. And yeah, however, there is now a distinction between active BCI and passive BCI. So active BCI is BCI that involves changing, modulating the brain signals, so they can be used, for example, as commands to control external devices or for communication. So there is a sort of active involvement of the individual, the user, to modulate or to produce only certain type of brain activity, while passive BCI is more about monitoring, for example, cognitive functions with a variety of purposes, but there is no attempt to change the neural activity or part of the neural activity. Simply the user, they will be engaged in whatever activity, and their neural activity will be monitored with any of the devices that for example, those I showed earlier. So there is now a definition, a broader definition of BCI, which actually was developed by the BCI Society last summer. And so they did a survey where they, because of course there is a bit of a BCI now is everywhere, and you find papers claiming to do BCI where it's more like neuroscience research. So they look at, for example, they look at brain differences in different conditions or in brain signals, but there is no actual BCI. So the definition, they did a survey, members of the public and members of the society gave their opinion. And so in the end, the definition was a brain-computer interface is a system that measures brain activity and converts it in nearly real time into functionality, useful outputs to replace, restore, enhance, supplement, and improve the natural outputs of the brain, thereby changing the ongoing interaction between the brain and its external or internal environment. It may additionally modify brain activity using targeted delivery of stimuli to create functionally useful inputs to the brain. A quite a broad definition, however, it's a definition that, for example, only clarify that it's only brain activity that is, when brain activity is involved, it's considered a BCI. For example, if peripheral sensors only are involved, are studied, then it's not really BCI. Well, for the society, it's a working definition, so it's open to interpretation as well. Yeah, and then it can include a simulation of the brain, but not necessarily. And this definition includes the most work on most traditional active BCI as well as passive BCI. How does a BCI work? So there are different approaches. Well, this is more about active BCI. So there is two main approaches to BCI. One is based to principles that are similar to neurofeedback, and they use like slow cortical potentials, mute synchronization, and mental imagery, typically. And this is called endogenous BCI. Endogenous because it involves the user has to modify their own brain activity with a number of strategies, different strategies, and I will show in a moment one of these. And then the other approach is based on event-related potentials, or this is exogenous BCI, because it's based on so the activity. The brain activity, the changes in brain activity, the different patterns depend on external stimuli. So it's not the user voluntarily trying to change some neural patterns of activity, but it's based on the external stimuli and the focus of a participant on some of the stimuli. So endogenous BCI, for example, is where a very typical approach is that it's based on mental imagery. So say, for example, that we want to control a robot or maybe a wheelchair, and there are, the BCI we produce can output 3 different commands: turn right, turn left, and go forward. So the participant, the user will think about 3 completely different things corresponding to each command. So a typical one is think about the right hand, moving the right hand, think about moving the left hand, and or the foot. So it's 3 different commands. A person has to be trained to do this. And of course, there will be the BCI will be trained to discriminate, to find the different patterns of neural activity corresponding to the 3 different thoughts, like right hand, left hand, and foot. And once the BCI learns to discriminate between these 3, then they can be used by the user to give these explicit commands. So always for when a person wants to use the BCI, there is a training phase where the user has to produce these different patterns, okay? And the BCI acquire all the data, all the neural activity corresponding to the 3 different thoughts, and then learns to discriminate between these 3. And then there is like a testing, an online, it's called, phase where there is no more training, and the participant actually use these signals to give commands, and there will be feedback about whether these commands are effective or not, how much the BCI has learned to discriminate between these 3 types of commands. It can be used a lot, this approach. For example, here is how it can be used for communication, so spelling letters. So in this specific study application, they have letters here and here that are scrolling continuously. And there are the user learns 3 commands. I think it's the selection, letter selection, and scrolling. Yes, left and right letter selection, and then scrolling. So like, I don't know, foot is scrolling, left hand is a selection of the letter on the left, and right hand is selection on the right side, so and so on. So, you know, this can be applied. Well, there are many publications about these approaches, and they may have very different interfaces, but the principle is always the same. Slightly different here. This is research from our lab. Quite recent. In fact, a new paper has been published a few weeks ago. It's a slightly different approach, but it's still about controlling different patterns here. The participants are trained to think about different concepts. And so the study is about the BCI has to learn to discriminate between these different concepts. The results, well, in this case, they have used EEG as well as FNIRS. There are very good results at the moment. I can't remember what the accuracy was in selecting the different words, but I guess, I don't know, 75, 80%, probably in a very, very limited categories. Yeah, so this is another example of how a user can use, well, another example of BCI based on endogenous, on the endogenous approach. And the other approach is that of using event-related potentials. So event-related potentials are signals that are produced in response to external stimuli. You might have often seen, is there a pointer? Well, thank you. Thanks. So you probably have seen, you might have seen this type of EEG activity representation. And so event-related potentials are specific peaks that are produced in response to simple stimuli. And you will, well, with filtering and averaging, it's quite easy to have these type of signals in response to simple stimuli. And there is one of the, so we have, there are, these different peaks have different, correspond to different stages in perceptual processing, and then higher level processing, like more cognitive processing. And one particular interesting signal is called the P300. It's P for positive, and 300 is because it occurs about 300 milliseconds after presentation of a stimulus. And this P300 is produced in response to something, or either an expected stimulus. So let's say that there is something repetitive going on, and then all of a sudden there is a change. Or similar to this, imagine a situation where there is many non-interesting stimuli, and then the person has to say when a certain target appears, then that's when a P300 will be triggered. And so here, these are typical cases of a P300 here, and no P300. So the paradigm is called, the typical paradigm which is studied is called the oddball paradigm. And there is a stream of non-target stimuli, and the subject is instructed to respond only to certain type of stimuli. And so if you average the responses to those target stimuli, you will have something like this. Non-targets will produce something like this. So no P300 or a very smaller P300. And so the same principle can be exploited. This principle can be exploited by ABCI. Again, if you type on Google, on YouTube, for example, if you type P300 BCI speller, you will probably see something like this, which is probably one of the most studied spellers, so used for typing letters on a computer. And the principle is the same, so of the oddball paradigm. So let's imagine, for example, that you want to spell the letter P. So you simply focus on the letter P and started counting, for example, mentally counting how many times the letter P appears. So mind that in normal circumstances, this is much faster. So you have something like 10 hertz, probably 8 repetitions per second, highlighting per second. So yeah, so every time the P is flashed, there will be something similar to a P300 that then with many repetition, the BCI will know that that's exactly the letter that you want to spell. And so that's what will happen. Just to give you an idea, however, how slow this is. So I was talking earlier about the I was talking earlier about the noisy signals. Okay, so the problem. So when you see those nice plots with the EEG signals, those are averaged over a large number of repetitions, and the signal have already been filtered. And this is a problem. So the noisy signal is a problem because with one single repetition, it's difficult to say, well, that was a P300, that wasn't. And so you need to repeat these the same many times. And that's why, so this is from our lab a few years ago, someone typing hi, I think was hi, the name of someone. And so you can see how slow the typing is, okay? Maybe well, using different methods, using better classification methods, better filtering, it can become faster, and probably is. But using non-invasive, when you use non-invasive devices like EEG, it's quite painful actually how slow that is. And so using the same principle in our lab, for example, we have developed cursors to move on the computer display. So here, for example, well, this is again very slow, but we have developed a mouse cursor that is made of little circles, and each circle represents a direction where one wants to move the mouse or the cursor on the screen. And so again, if you focus on one of the circles representing the direction, say that I want to move it up, then again, using the same P300 principle, the mouse will move up. Yeah, so as I said, these are very slow. The BCIs are very slow, and they can be good if you if they are used by individuals with very severe motor disabilities, and that's their only way of communicating. So having something like this is better than nothing. But for everyday life, of course, it's not good, and which is why these devices are not really used, are only tested, used in everyday life from patients with, for example, locked-in syndrome. Much better results, however, can be obtained when you use invasive devices. And there is quite a lot of work at the moment, quite a lot of research on speech decoding. So speech decoding, which can involve decoding, depending on the brain area, but decoding actual phonemes. So one thing, the user thinks about words or sounds or sentences, and then through quite advanced machine learning techniques, this can be actually translated then into actual speech. So these people, like for example in this publication here, there is a patient with an implanted device, which I think it was ECOG, which they have so they have developed a BCI for producing sentences. Again, the user has been trained to think about the sentences over many sessions. So that's one of the problems. It takes many sessions and repeating all the same for many sessions before BCI can actually learn to discriminate between the different patterns of neural activity. What was particularly interesting about this patient was that so in the study, to use this BCI, the patient has to think about what they want to say. And then I think they had the electrodes implanted in the sensory motor cortex, if not, I'm not confused. So the interesting thing is that that patient hasn't been, when he took part in this study, the patient hasn't been speaking, hasn't been able to speak for quite many years, like 15, 20 years, but still, and that, so it's not clear whether, for example, the neurons rewires in a way that there is no anymore a correlate of the actual pronouncing and saying the sentences, saying the words. But actually it worked. Despite of this, it still worked. So yeah, so this was quite a successful case of use of exactly implanted devices. One of the problems with the implanted devices is that they can only use in some cases, well, because it depends where they are implanted, so what part of the cortex they are into, and that limits the use of these devices. Okay, so these were examples of um, BCIs for communication with non-invasive and invasive devices. But as I said earlier, there is also an area of BCI that is called passive BCI. It's very similar, and it's sometimes there is no really difference between BCI and neuroergonomics. So also neuroeconomics is an area of using neurotechnologies in everyday life for improving, basically, for example, the conditions of people at work or doing everyday tasks. For example, someone who's driving a car or a pilot of an aeroplane. So it's a lot about tracking, monitoring the mental state, the vigilance levels, attention levels, memory, and so on. Yeah, so there is quite a lot of research around this concept nowadays. And if you look at passive BCI neuroergonomics, you will find many, many publications about this. Yeah, and yes, another typical case is that of monitoring the mental workload. So how tired is a person? Is it too much? What they are doing? Do they need a break? Do they need someone to help, for example? So this is a typical, this is from Arico et al. In 2017. They have developed a system for monitoring the mental workload. And so how the system works is that there is a device monitoring the neural activity. And then while the person is doing a task, for example, I don't know, let's say someone checking, the air traffic controller, for example, where they have, a lot of information coming through, and they have to be vigilant all the time. So the device monitor their mental, the BCI device monitor their mental workload, and then the computer, the system that they use for acquiring information, checking information, will adapt. So, for example, there are things you can do, things like changing the interface, changes in the task, taking a break, or neural stimulation, depending on what the tracking of the mental workload is saying. Is it too much? Is it too tired? And so on. Okay, so I would like just now to present some of the research that I've been doing with some of my collaborators in the Essex BCI lab in the last few years. We do a lot of work on using BCI for decision making, in particular for group decision making. The idea is that because of the problems, well, the first idea was that I talked about the need of repeating the same stimuli over and over again because the signal is too noisy. But the idea originally, at some point we thought, okay, what if we actually put brain together? Instead of repeating the same thing, we have many people looking at the same thing. Maybe the BCI would be faster at recognizing a stimulus or controlling a cursor and so on. And so we first tried, that. And we tried it with I don't know, earlier I showed an example of a cursor based on the P300. And so we tried this concept applied to the use of a spacecraft simulator, a very simple one. So the purpose is to drive a spacecraft to a planet, which is the white thing here. And then the spacecraft is traveling towards the planet, but it has to be steered at the right, to the right direction. And so the mouse, the original BCI mouse, was then used to steer the spacecraft. And then, but instead of having one person doing this, we had two users together doing the same task. And that was great. I mean, we had, well, we tested quite a few pairs of participants, and for some pairs it was mixed results. For some pairs it was definitely much better. However, well, it's a lot. It requires a lot of concentration. It's not practical, and it's still much slower than using the actual manual control, of course. So we kind of abandoned this idea. However, we actually, by working with combining signals from different participants, we realized that actually we can, there is a good use for this approach. And we came up with the idea of collaborative decision making. So we all know that groups can do better than individuals in many cases, for a variety of reasons: information, body language, a lot of different things that contribute to making a decision-making group more accurate, typically, than the same decision taken by individuals. However, there can be problems with groups, and groups there can be biases, there can be strong leadership, time constraints. So if you have to make a decision quickly, communicating becomes difficult, and there are misunderstandings and so on. So we thought, well, look, actually, we started seeing from a simple experiment that I will show in a moment. We thought, well, actually, we might be able to get neural signals that are an indication of how confident a person is about their decision. We know that it is possible to, so the confidence in a decision modulates some of the neural signals. And so we could use these neural signals then to weight the individual response within a group, and then combine a final decision. So, and that's what we do. We have participants doing a specific task. They have an EEG. Each participant will have their own BCI. So, and the BCI, what it does is it will monitor the confidence based on not only neural signals, but we also take other behavior information. So the BCI takes in the EEG signals. The person, they are responding to their task manually. So it's not just about neural signals. We also take a lot of physiological signals, and then the BCI will assess based on response. So, for example, when people, when they are more confident, they respond faster. And also the neural signal changes. So the BCI combine all of this information and assess the confidence of the participant, and it does the same for each participant. And then they combine all of these confidences to make a final decision. We applied these to different tasks over the years. sorry, just checking. I forgot something. Okay, sorry. I hope this is quite clear. But I'm happy to describe this in more detail later if you're interested. But we have done a large variety of experiments. We started with very simple, like target detection tasks here, and then visual matching tasks, so saying whether patterns of shapes and colors are the same or not, visual search. And then we changed into more realistic tasks, like, for example, here, detecting a person within a crowd. And here we use videos, and now we are working on more strategic decisions. Well, we are doing experiments currently with, I don't know if you are familiar with the pandemic game. It's a board game. It's also, and so we use this pandemic game, which is about, well, it's a pandemic spreading everywhere, and the user have to assign resources to the different places and trying to contain the spreading of the pandemic. Yeah, so we have done, we don't have yet good results here. And yeah, so it's doing more strategic and decisions made on a longer time window is not, we realize that neural, correlates of, neural correlates of confidence are not as clear as we had in previous tasks, where the task is simply for example, saying target or non-target, or yeah, was the person, was the person there or not? So there are, it's much more complicated. I will show you an example of, sorry, I'm a bit late. I will show you an example of one of the experiments that we did, which is about doing, well, it's about finding whether a polar bear was amongst the penguins. We know that polar bears and penguins don't live in the same place, but that's how our PhD student came up with when he designed the experiment. So the purpose was to have like more realistic images rather than very simple shapes and so on. So now we tried the task, just one presentation. It's very fast, so you won't see anything, I can promise you. But if you're ready, now I will. So did you see the polar bear or not? Did you see anything at all? There was something. There was something, yeah. Yeah. So there was, this was the image. Was the polar bear there? Yeah? Okay. So let's try again. This is the different image now. Was it there? You didn't see anything again. Okay. Right. Can you see the polar bear? It's a smaller polar bear or giant penguins. So yeah, so we did so we simulated a group. So what we do is participants play this individually, and then we combine offline the different groups, simply because we present the sequences of stimuli always identical. They are always identical, so then we can combine offline all the different combinations of groups of different sizes. Okay, so here just briefly, it's this graph most shows the errors, okay, percentage of errors. Blue lines, the lines here red, are different combinations of BCIs using different features. The black line shows just a simple majority vote. So taking the most popular choice, whether the bear was there or not, yes or no, and so we are able to improve the decisions particularly for even size groups, simply because the BCI makes a difference when there is a draw. So for example, two say one thing, two people say one thing, and the other two says something like that in a group of four, the same choice in a group of four, and so the BCI then is able to flip the decision to one side or the other. We used other tasks, like this one, for example, is about so from time to time there is a soldier like crossing the corridor, and participants have to decide whether it's wearing a helmet or a cap. Here, if you look, what we do is we train an algorithm to discriminate between correct and correct responses. And so here there are differences in around the response between in the neural signals, and that's how the BCI is able to discriminate between, well, to assess whether the probability of the choice being correct or incorrect. And here, other experiments with similar approaches. And this is what we are doing now. So experiments using a pandemic, the pandemic task. Yeah, I'm not describing this because we don't have time really. But there is a lot more about using neurotechnologies for cognitive enhancement. I didn't cover anything, for example, about neurorehabilitation, emotion recognition. There is music therapy, memory enhancement, a lot of them. Yeah, so here is an interesting study about memory stimulation, well, using implanted electrodes for improving memory in patients. This is from our lab, Ian Daly, doing the studying affective brain-computer interfaces. So using music therapy based on the neural response of the, well, based on assessment of the emotional state of a patient from the neural signals. Here, Sebastian Halder in our lab is working on using EEG signals to assess consciousness level. Anna Matrang is working on memory encoding. So again, being able to detect whether a person remembers something or not. And then other areas include hyperscanning, very fascinating area. Using neurotechnologies for neuroscreening, so selecting, for example, personal selection based on neural responses to whatever. It can be to the ability to stay vigilant or to respond to memory tasks and so on. Here, just a screenshot from a report from Neurotech Analytics in 2021 showing, if you're interested, it's a very interesting report in the state of private investment companies investing in neurotechnologies. So you can see how it's increasing. Yeah. And yeah, finally, neuroethics. Yes, of course, the use of production of all these neural data needs to be regulated. There are many problems about, for example, data sharing and privacy. Well, mental privacy, the safety, invasiveness of brain stimulation, for example. Problems about, for example, when we use BCI for controlling an external device, the problems, issues around agency, responsibility, and liability. So if I use a BCI user for, I don't know, controlling a prosthetic arm, and I got the movements wrong and something happens, who's the responsibility for this? Is the user's responsibility? Is it the developer responsibility? Is the algorithm? So this is all things that has to be clarified. Concepts around personal identity, like think about people with an implanted device and like, yeah, the device helping stimulating, I don't know, the hippocampus and improving their memory. So what about does the personal identity change in this case? And similarly, free will. And then, of course, the cost of the society, because this research is very expensive, requires a lot of investment in public money. And if one day these technologies will be really accessible and usable in everyday life, well, how about, access, who can access to these technologies, and will this create even more division in the society? This was about what we were discussing yesterday. So in China, there was this. It was a few years ago, all over the news of portable EEG devices used to monitor level of attention in children at school. This morning I was looking into this and discovered that it was this has been suspended exactly because there were too many problems with privacy and data sharing and all of that, and the unethical use of that. Okay, so just a few closing comments. So there is quite a lot going on with the neurotechnologies for cognitive enhancement. There is, I think, a huge gap between, as researchers, what we know that neurotechnologies can do and the public perception of like these science fiction abilities of these technologies. Maybe we will get to this like science fiction scenarios, but we in the labs, we struggle to do even things like monitoring attention. It's a hard task, and being able to do this consistently and accurately in an everyday environment is a real challenge. So yeah, maybe we will get there soon, but it's still quite hard work. And yeah, well, thank you very much. So this is our lab, the QR code to our webpage. And if you're interested, we do well, we have a LinkedIn page, and we do seminars every month. So if you go to if you like the LinkedIn page, you will find out about our seminar, monthly seminar. Thank you very much, everyone. Sorry for the long talk.